Okay, so here, what state the laws of electromagnetic induction? Well, there's two. There's Faraday's law and Lenz's law. So, I think this is what they refer to. I think this is what they mean when they say laws. I'm not 100% sure the plural. So, the two I always think of is Faraday, which basically says the induced voltage will equal to minus the change in the magnetic flux per change in time. So you can say that out as a sentence. That is the induced voltage in a conductor in a conductor exposed to a time varying magnetic field is proportional to the rate of change of magnetic flux per unit time. So just to fix that formula up as a proportional formula, the induced voltage, perhaps EMF would be more appropriate to call it, is proportional to the change in flux per second. And Lenz's law, Lenz said that the induced current will oppose the magnetic field that created it. So that's important for the second part here, part 2 and 3. So what's going to happen here if you put a piece of copper here? What will happen is, number one, the magnetic flux will vary due to it just oscillating, due to the magnet oscillating. The magnet oscillating. Two, Faraday says that a current will be induced in the copper. 3, Lenz said that well, actually it's not really Lenz, this one here, but it's just the fact that, I don't think it has a name, but it's the fact that a current, the induced current will have a magnetic field, basically. The induced current will have a magnetic field, will have a magnetic field around it. And now we can say for Lenz's law implies that this induced field will oppose the original field. This induced field opposes the original oscillating field. And then this will create a sort of friction, type of friction. Create a, I think you would call it a retarding force. And you could say, therefore, it will quickly stop swinging. So in other words, putting the copper here will cause the periodic time to be less than normal. It's damped. It's a damped motion. It will quickly come to rest. Describe what would be observed if instead plastic was placed. Well, I won't write out everything again, but if plastic was placed there, 2, 3, 4, and 5 and 6 is gone because there is no conductor to have an induced current and so on. So it just basically then becomes a simple pendulum. Not damped. That's just the short story, because all these steps are now gone because plastic's not a conductor. So yeah, that's really it. Okay, so I'm not sure if I got everything right here. The laws of electromagnetic induction. I mean, there's other laws too, like, you know, left-hand law, right-hand law. I mean, given what the second part and third part is here, I feel like maybe in part 1 you might want to also mention the right-hand grip law. I think that might be relevant to part D. Right-hand grip law says that if you hold your hand as if you're gripping the wire with your thumb directed in the direction of the current, the magnetic field will be in the direction of your fingers. Perhaps they would like that mentioned in part 1 as well. 12 marks. Maybe they want 3 laws here. 4, 4, 4. That would be the only other relevant law here. That's what I'm basically mentioning in part 3 here. So you have Faraday, Lenz, and the right-hand grip law. Perhaps those are the 3 they would like mentioned in part 1, since you need them in your explanation of part 2. And part 3 is the simple part. It's just literally a simple pendulum. Okay.